right, hello everyone. Please welcome Saul with his talk, same API, different execution. Saul is from QuantSight, so give a round of applause and I guess we'll start.
Hey, thanks everyone for being here. I'm really excited to be here with all of you and share some work that we've been doing at QuantSight for the past year or so. So I'm going to start. This is just a little preview, so I'm not going to go over right now, but it was just to kind of whet your appetite. And I'm going to start with just some Python code. We're going to go into some history that might be relevant. And then we're going to come back to this example and back to MetaDSL, which is this framework that I'm going to be talking about today. And just to situate the talk, the goal is thinking about the future of data science and machine learning in Python, and making sure that Python is still performant and accessible to new users moving forward in the ecosystem. So it's a pretty broad kind of category, but this is kind of an approach that I'm going to be taking, and I'll show you why maybe it's useful. If we look at this function, can you all read this in Python? Is this big enough? Yep. So what we're doing here is we're creating an array of a bunch of numbers, we're adding them to themselves, and then we're indexing. So this code is probably looks pretty normal to all of you if you know Python. But I want to highlight sort of something about it here, is that we're making a separation between allocating our memory, doing our computation, and then saving that to a result, and then doing some more computation. So it's a very sequential kind of process, right? Python is like you're doing some work, you save it to a variable, you do some more work, and you save that to a new variable. And if we look at sort of like time, right? We think about we're allocating, this range of numbers, we're adding them, and then we're indexing them. So if we want to say, let's make this code faster, right? What can we do? Well, we can make each of these steps take less time, right, by running less instructions on our computer. And so this is what NumPy lets us do, right? This is a lot faster, but it looks very similar. We're allocating a bunch of memory and filling it up. We're doing some operation, and then we're indexing again. So we have a similar kind of structure where you have time going down, and your computer is doing things sequentially, but we're just compressing each of these operations so that they run quicker, right? And so this is how we can optimize like our scientific code with like our existing NumPy kind of SciPy stack. Thanks. Yeah, that's useful. Look at that, how fancy. Sweet. So this kind of architecture is called the von Neumann architecture. And so, let's scroll down a little. We see this kind of like pipeline here. We have our CPU, we have our memory, right? And so we're going back and forth between our CPU and our memory. We're fetching an instruction, we're generating the data that it's operating on, and then we're performing that operation and we're storing the results. So this fits, if you know Python, this fits kind of like in our mental model of how Python works and how many programming languages today work. So this is just stealing from Wikipedia. You say a von Neumann language is a language that kind of copies this architecture but at a higher level. Right? So this is kind of how we're used to computing. And so this is, let's make this bigger. So this is great. We can increase our performance by running our instructions faster, right? By getting new hardware, CPU that runs faster, or we can run less instructions, right? And so this is the NumPy approach, right? We're doing the same work, but we're actually running less instructions on our CPU, so it grows quicker. So we're going to look at a couple issues with each of these points here and why that might need changes in the Python ecosystem to accommodate like going forward. So the first one is hardware slowdown, or hardware is not getting as quicker anymore as like it was. So you see here, this is the frequency of your CPU. So like 3 gigahertz, 2 gigahertz, that kind of thing. We can see it's pretty much flatlined, right, in the past like 10, 15 years. We can also see like single thread performance. So this is if you're just running a Python program. It's also like flatlining. And so you see though that there's actually transistors. So the number of like little hardware units to do computation is still going up exponentially. So what's going on? Why aren't our chips getting faster? Well, we're getting more cores, right, to do our work. So this is why you see things like multi-core, and then other kinds of. Let me pull this up. Yeah. So this is. There's some kind of like physics behind this and some computing laws about it. Like you might have heard of Moore's law or Dennard scaling, and that kind of captures these relationships. But as those are ending, we're seeing a switch to multi-core processors. And so we see a bunch of other things as well, right? We're moving to GPUs, multiprocessing. We have more caching. We have pipelining in the CPU, where it will try to execute a bunch of instructions at the same time and hope that one of them is the one you wanted, right? So these kind of like things that really break with our mental model of how Python works and how a von Neumann machine works, because it's no longer just run this, save it to memory, run this, save it to memory, right? We're having parallelism, we're having different types of hardware that aren't represented by this architecture. And so we call this von Neumann machine, right? We have the processor and the array. We can call this kind of like the slowdown that happens when we try to keep doing more operations, the von Neumann bottleneck. And back in 1977, John Baucus was, as he was accepting his Turing Award, he was complaining about this bottleneck, not just because it was slow, physically, but because it was an intellectual bottleneck, because it encourages you to think about one operation at a time. Right? Instead of thinking about your whole program as a unit, you're thinking about, hey, I have this one A range, can I speed it up in NumPy? I have this one add, how do I speed this up? Right? So it encourages you to think in these little blocks, and it doesn't let you make the kinds of optimizations that you need to really get increased performance and optimize this hardware, right? So this has also had consequences, right? The software is responding to this. So this is some GIF from the TensorFlow website on some kind of idea of how their TensorFlow graph works. So if you haven't used TensorFlow, it's a deep learning library, and it lets you write machine learning models. And the difference between it and something like NumPy is that it represents things as a graph, right? You represent a graph of your computations in some way, and then you execute them as one. So it lets you talk about this this larger conceptual unit than just a single operation or like a block of operations, right? So it has, they've found it very useful in being able to then compile to different architectures. So the reason why TensorFlow uses this is so that they can then distribute your computation or compile it to GPUs or compile it to other hardware that's not based on the von Neumann kind of architecture like Python is. So this is harder, like it's more complicated, right? This is like a more complicated world that we're moving into than the sort of where we have been in 10 years ago or something, because we didn't have to worry about parallelism and all these other kinds of different hardwares. So this is a little visualization I tried to put together, looking at if you're starting in Google land in Python, what are the different types of hardware you can hit? And what are the different, basically the different graphs or different frameworks that you need to target to get high performance? So you notice here that Intel has its own framework called ngraph, which is like a TensorFlow graph, but it's specific for Intel chips, basically. So if you want to run on their special new neural network processor, you have to get your code into ngraph first, which is its own representation of how you're going to do your machine learning model, how you're going to do your computation, right? And same for AMD, ARM, and NVIDIA. So the point is that as a developer, you don't want to have to care about this, right? You don't want to have to think about, oh, I need to rewrite all my code so that I can use this new NVIDIA chip that they just released, right? That's not how it is today. You just use NumPy, and they can compile a new version of NumPy for a specific CPU processor, and you can get increased performance without having to change your code. And that's how it should be for this kind of graph-based layout as well. You should just write your code once, and then be able to target all these different intermediate representations that are coming alive in these different hardware. So then I want to connect this to the community open source, right? Because there's a lot of things we love about, well, the reason why we're here is not just like the technical details of how to do this, but it's that we're doing it as a community. We're doing it in a distributed manner. It's not just one company coming and saying, well, we built this stack for you and it works great and we can target all this hardware, just buy into what we, kind of our way of doing things and you'll be fine. Like that's not the world that I want to live in, at least. So we want to be able to support, all these kind of diverse libraries that all build on each other, but still be able to target all these different types of hardware in a performant way today and into the future, right? So we want Python to still be a language that people are using to write high-performance computing, machine learning software, but we don't want it to be consolidated all within like one stack, right? Because it's a hard problem, we haven't decided to solve it as a community. And so there are, Dask, right, Numba, these are solutions to this, but using them together, like today as a user, is not always, it's not always obvious how this fits together as an ecosystem, right? Like how do I use scikit image on a distributed manner with GPUs, right? It's a lot of work to do that today. There needs to be sort of like, so what we need is kind of software to bridge the gap where we can represent all these different libraries and they can play together. So that's what I've been exploring, at least, with this MetaDSL project for decentralized cooperation on solving this problem. Sweet. So yeah, we have tools. Yep. So I'm going to show a little example of a fake array API. We have a get item, we have an add, and we can make arrays with this arange function. One thing you might notice is that there's no actual definitions here, right? This isn't saying how these functions are computed. It's just specifying the API for this mock array library with using Python's typing, right? So we can, and then we can write a function like this that takes two arrays, adds them, and indexes. And we can actually call that on arange. And we have this sort of, what will be computed. Right? We have a representation of what we want to compute. We don't know how to compute it yet. We don't even know, should we run this on Python? Should we run this on TensorFlow? I don't know yet. At this point, all we have is a description of what we want to compute in Python, right? And so is this, can people see how this translates here, or are there questions there? I've been looking at this for a while, so for me it's, makes sense, but I think, yeah, please let me know if you have any questions.
Why does it read that only have one load attached?
It is two. This is slightly darker.
Okay.
Yeah. That's a good question. Yeah. So let's see. So then we might say, okay, so we have this kind of abstract representation of what we want to compute. Now let's actually use NumPy to compute it, right? Because we can use NumPy to do these operations. So here is where we start to get interesting. Now we can start to say, hey, we have we can create an array from a NumPy array. And then we define how all these rules work on arrays of NumPy arrays. So we say, hey, if you're taking an arange of something, turn that into calling NumPy arange, and then turning that into array. If you're adding two arrays, add the inside NumPy arrays, and then turn that into this array that we've defined, right? And same for indexing. So now, if we execute this, we see we get a result. And not only that, we can step through this execution, and we can see, oh, well, before that, it was calling getItem, right, on this array. And before that, it was adding two arrays. And then we can see our initial, right, is what we had before. So we can see how we start from this kind of abstract representation. And then we, through executing these replacement rules that we've defined here, we can get to our result. And so the key point is that this the person who writes this could be a different person than the person who writes this. So one project could write an interface and another project could write a backend, and we can separate that work out, but we can still cooperate as an ecosystem together, right? And the user can still use the same function, right? They're still using this function here. They're doing the same thing here, and all they have to do is import this library or set some config or what have you, and they can run their code. So as a user, you don't have to depend on the specific implementation. You just depend on this generic sort of the API, right? That's you depend on the API, and then you can import libraries to define different ways to execute it. So another advantage, so this is like computing it eagerly with NumPy. We can also see sort of how we might compile this in some way, right? So instead of creating an array from a NumPy array, we're going to create an array from a string. So here we're passing in some symbolic array, a maybe, to this function. And instead of, so we say if we're adding two symbolic arrays, we're just going to create a new string that has the addition. And if we're doing indexing, we're creating a new array that has the indexing. So then the result that we get is this string of adding two arrays and then indexing. So this is kind of a toy. This is definitely a toy example here. But instead of creating a string, right, this could create LLVM code, or then you could eval this string in Python. So what you end up as a result here is not actually a result. It's a compilation of what you want to do, right? So you're separating out, hey, this is what I want to do, and this is I've compiled it in some way to some form. And this could be a TensorFlow graph, right? So then you could then send this off to TensorFlow, and it could execute it. So that's kind of the vision that we're moving towards. And the other advantage of having these things in a symbolic form is that then we can write optimizations, right? So here we might notice that we're adding two arrays and then we're indexing. So that's a bit inefficient. So instead, we can index first and then add, right? Because if you're adding first, you're doing all these additions, and then you're just picking out one element. Like you didn't need all those other, you needed to add all those other elements. It's kind of a waste of time. So instead, you can index first and then add, and then you're just getting the result that you need. So this is kind of an example of how looking at the program as a whole, right, can give you more optimizations, because you can do less work if you look at the larger chunk, right, the larger conceptual unit than just the little operations. So we've defined this rule here, and then if we execute it, we see we still start with our original array here, but our first rule is this optimize, right? So it's switched it, so now we're doing a get item. We're doing adding a get item instead of get item and add. And then as we compile it, we can see we get this array here, right? So we're indexing first, and then we're adding. How am I doing on time?
Good.
How much?
You have 12 minutes.
Okay, sweet.
Sorry.
Okay, great. Then I'll go into this. So the other thing, so this kind of optimization is still very specific, right? Like we wouldn't want to have to write this kind of optimization for every array operation, because it's like you could, kind of invent any number of these types of things to replace. So instead, what we can think about, we can think about our arrays as functions themselves. So here we're defining a new array API that's abstract, and we're saying it has two methods, right? It has a shape, and it has this indexing method, and it has add. So it has three methods. And we create it using a shape and a function. So instead of thinking about array as like a chunk of memory, we can think about it as just a mapping from your indexes that you provide to the value, right? So for like a range, you pass in, you index 2 into a range, and you're going to get 2 back, right? So you can think about it as a function mapping your indices to the values. So if we represent our arrays like this, then we can kind of get these types of optimizations for free, because what we end up compiling is a function that represents our final array, right? And it squishes down all the operations into just one array. So we can see this for this example here. We can define, the shape and the indexing function. And then we can define how to convert from our original array to this abstract array. And then when we start initially, right, the same thing that we have, but when we run it through this kind of replacement, we get back some abstract array A, and we're indexing it by 5. And in this case, now it's a vector of integers, and we have 5 here, and then we're adding it. So we've gotten this optimization out that we wrote above manually for free here, because we're thinking about arrays more generally and more mathematically than we were before. So the point is that if you can start from one kind of array here and end up in another kind of array. So you might have your NumPy API is this initial one that's for users, and then as you're doing your replacements, right, you end up in another API that's more suitable for compilation and for optimization. So you can have these different stages and these different representations as you're moving along the pipeline, and different people can maintain all of those and define translations between them, right? There's this great blog post about Guido, and I love this photo in it. So I wanted to end with this photo and a quote from Computing for Everybody, the grant that he wrote in the early 2000s, where he said, "We're looking forward to a future where every computer user will be able to open the hood of their computer and make improvements to the applications inside." So I think this is really applicable to our ecosystem. Like, we want every user to be able to open the hood to their machine learning pipeline, to their data science pipeline, and make improvements inside, right? Personally, I don't want to live in a world where there's one, group of people making the optimizations and building the frameworks, and another that are users that have no control over, what they're doing or optimizing it. We should be able to share those responsibilities and be able to cooperate on, building these optimizations together as a community. Because I think that will lead to more innovation and, just more interesting work. So I think I have some time for questions. Thank you.
All right, whoever has a question, just raise your hand up. I'll give you the microphone.
Very interesting work, pretty advanced language engineering there. If I understood correctly, there are two kinds of rules. There's one where you're essentially writing overloaded operators. And then the second kind where you're rewriting something that was already written in a different syntax. Can you clarify the interaction between the two?
Sure. So there's just one real type of rule. Let's go back to this example. So everything in MetaDSL is an expression. And so you build up, normally in Python when you call functions, right, something happens. Instead, in MetaDSL, all you do is you record, I call this function with these arguments, right? And so this builds up a graph of what you want to do. And then you write rules that say, when I see this thing in the graph, replace it with this thing in the graph. And we have a helpful way. Let me go back to this one. I think it's nice. So here you can see this is a rule, and this is when it sees this in the graph, it should replace it with this, right? So the nice thing about this is this all checks with MyPy, and it just looks like you're writing Python. You don't have to learn a new meta-programming kind of language. You just write, when I see this, I want it to be replaced with this, right? So that's the entirety. That's like all MetaDSL gives you as those 2 blocks, really. And then what you do with it, like what kinds of domains you build, how they translate between each other, is the problem that we have to solve together, right? And that we have to figure out. I don't know if that
made it
a little clear.
Any more questions? We have a lot of time, so, well, not a lot of time, but.
So maybe to give you a sense of where this is heading next, I don't know if any of you know MLIR is a framework from Google that does something pretty similar to this. So it's coming out of Google Brain or Research or something, and it's a way to represent different intermediate representations, like TensorFlow graphs, LLVM, because they have so many different, like if you go back to this, this isn't even showing all of their things, but you can see here they already have TensorFlow graph, XLA, and they have all these other representations, and they need to translate between them as well. So even just inside Google, this is a problem for them, for their internal ecosystem. So they're building this tool MLIR to handle this. So I want to look at integrating with that or seeing, what are the similarities there. It's like a C++ first tool, and this is like a Python first tool, so there might be some differences, but they have a similar intent. And then otherwise, really, we're just looking for use cases. So if you have a problem space or you maintain a library and you are thinking, hey, this library is great, or I want to solve this problem, but I really need to target, I need to target different backends, and I don't want the API to be tied to those backends directly. Like if that's how your problem is looking and you need high performance, then I think this might be useful for you, and we should talk about it. So, yeah.
All right, if we have no more questions, just give a round of applause to Saul. Thank you.